Good morning, evening, afternoon, whenever you're watching this, and welcome back. Today we're going to continue our exploration of some more advanced integration techniques, and today's video is going to be all about trig functions. So be ready to see a bunch of sines, cosines, tangents, your favorite functions. We're going to learn a lot how to integrate integrands that have these functions in them, and by the end of this video, you'll be an expert at them, or at the very least, you'll have a good set of resources to approach these kinds of problems. So let's get into it. Integrating trig functions with powers. So in general, when we see integrals of this form where you have trig functions raised to some powers, it's common to use u-substitution or integration by parts, some of the techniques we've already seen thus far. Since trig functions are so unique, it can also make integrating them kind of tricky. So for that, we need to have a good set of tools in our toolbox to approach these problems. So it's important to be familiar with some of your trig identities, the ones shown in the slide being the most common ones. First, you have sine squared x plus cosine squared x equals 1, very helpful. And then you have your half-angle formulas. Sine squared of a of x equals 1 minus cosine of 2ax divided by 2. Cosine squared of a of x is pretty similar, 1 plus cosine 2ax over 2, so the difference being this sign here. These are the half-angle formulas. You may have seen them as like sine of x over 2 equals the square root of 1 minus cosine of x over 2. These two are identical to each other. It's just a little bit of manipulation, squaring both sides and then handling the coefficients separately. That's besides the point. But yeah, these are the formula to be familiar with because we'll be using them quite a lot. Now, I'll give you a set of guidelines for evaluating integrals with sines and cosines. This is sort of like a checklist of how you should approach some of these problems, and I find this extremely helpful. So first, if one of the powers is 1, try using u-substitution. So if you have something like the integral of sine of x times cosine cubed of x dx, try using u-substitution since the power of sine is 1. If the power of sine is odd and positive, so say it's sine cubed x times cosine cubed x, then you're going to save one sign and convert the rest to cosines. So what I mean by save one sign is we're going to change the sine cubed of x into sine of x, which I'll underline in pink to indicate that we're saving it, times sine squared of x times cosine cubed of x. And then we have to convert the rest of the sines to cosines. We see a sine squared x. We can convert it to cosines by using this identity here, where sine squared x is 1 minus cosine squared x. So this would be equal to the integral of sine of x times 1 minus cosine squared x times cosine cubed x dx. And this final integral is much easier to solve, actually. You can distribute the cosine, multiply the sines through, split it up into two integrals, and actually do u-substitution to solve them. We'll see a problem similar to this a little bit later. Third guideline. If the power of the cosine is odd and positive, then save one cosine, convert the rest of the sines, and solve as normal. So very similar thing as I just showed. If the powers of both the sine and cosine are even and non-negative, then you'll want to use the half-angle identities to convert the integrand to odd powers of the cosine. So there you go. Those are your 4 things that you can look at if you see a problem. Hit one of these guidelines and then just follow it. So again, I have some of the formula to be familiar with. This is the main one, sine squared x plus cosine squared x equals 1, but you can always solve for sine squared of x or cosine squared of x. So that's what we did here. We solved for sine squared of x and plugged in 1 minus cosine squared of x. So here's a little example. I kind of just showed one before, but this one is a little bit more in depth. We have the integral of sine cubed of x times cosine to the 4th of x. So if we look at our guidelines, the first guideline, if one of the powers is 1, try using u-substitution. Well, the powers we have are 3 and 4, so we can't follow that guideline. If the power of sine is odd and positive, save one sign and convert the rest to cosines. Well, the power being 3 is odd and it is positive, so we'll follow that guideline. And just like I showed above, we will save this sine of x. So we'll make sine cubed of x sine x times sine squared of x. Since we're saving that sine of x, it's going to remain, but we're going to convert the rest of the sines to cosines using that identity. Finally, we'll distribute the cosine to the fourth x into these other two terms. So we have sine of x times cosine to the fourth of x minus cosine to the sixth of x. We can now distribute the sine into both of these terms and then split up the integrals because there's going to be a minus sign in between them. So we have cosine to the fourth x sine of x dx minus integral cosine to the sixth of x times sine of x dx. And we can actually solve these integrals simultaneously by using u-substitution, since they'll have the same u. We'll let u equal cosine of x, which means du equals negative sine of x. For the first integral, we have u to the fourth for cosine fourth of x. We keep that sine of x. Replace d of x with du over negative sine of x. And for the second integral, a very similar thing, where we see things lining up here. We'll see that the sine of x's cancel, and then we're left with an integral in the u world, which we can easily integrate using the power rule. So this is our final value. Substitute u back in. Substitute u back in, and then we will get our final answer here. That's the general workflow. This is a worked out example, but we're going to try to do some examples on our own in just a little bit. But as you know, sines and cosines are not the only functions that exist in the trig world. Sometimes we see secants and tangents, and we know that those also go hand in hand due to the identity secant squared of x minus tangent squared of x equals 1. And of course that derives secant squared of x equals 1 plus tangent squared of x, and tangent squared of x equals secant squared of x minus 1. Here we have some more guidelines when we see problems with these. If the power of secant is even and positive, then we'll save a secant squared factor and convert the rest to tangents. So if we see something like, the integral of secant to the fourth of x dx, the power is even and positive, so we want to save a secant squared term. So we'll convert this into the integral of secant squared of x times secant squared of x dx, and then we'll convert the rest into tangents. So this will be the integral of secant squared of x times 1 plus tangent of x, 1 plus tangent squared of x dx, and then integrate from there. So similar thing with sines and cosines, just now we're saving a secant squared term instead. Second guideline, if the power of tangent is odd and positive, then you'll save a secant times tangent term and convert the rest to secants. The rest meaning tangents. Here, this rest means secants. Guideline 3, if there are no secants and the power of tangent is even and positive, then you'll convert a tangent squared into secant squared minus 1, using this identity down here, expand, and then repeat as necessary, because we have just tangents to deal with, and when we reduce it, like if we have tangent to the sixth of x, we break that into tangent to the fourth of x times tangent squared of x. We convert the tangent squared into this, but we still have a tangent to the fourth of x, so we might have to break that up into tangent squared. So that's what we mean by repeat as necessary. Number 4, if the integral is only secant with an odd positive power, then we'll have to use integration by parts. Finally, if nothing works, then try converting the secants and tangents into sines and cosines. Remember, secant of x is equal to 1 over cosine of x, and tangent of x is equal to sine of x over cosine of x. So sometimes we might see that converting it to sines and cosines makes it easier because things start canceling out. And the similar thing goes when you see cosecants and cotangents. It's probably easier to just convert everything to sines and cosines and work from there. And here we see an example with secants and tangents. So we have the integral of secant to the fourth of 3x times tangent cubed of 3 of x. Let's look through our guidelines and see which one to use. If the power of the secant is even and positive, which it is, then save a secant squared factor and convert the rest to tangents. So let's do that. We break the secant to the fourth of x into secant squared of 3 of x times secant squared of 3 of x. This is the one that we'll save. We'll convert the rest of the secants into tangents. So for that, we'll use our trig identity, saying that secant squared of 3 of x is equal to 1 plus tangent squared of 3 of x. Now, just as we did in the sine cosine example, we'll distribute this term into the parentheses, this tangent cubed term. So we get secant squared of 3 of x times tangent cubed of 3 of x plus tangent to the fifth of 3 of x. And again, we'll distribute the secant squared term in and split up the integrals, and we're left with this sum of two integrals. And again, we can use u-substitution to solve this. In fact, we can do it simultaneously. We'll let u equal tangent of 3 of x, which means du equals 3 secant squared of 3 of x. So this is why we see we wanted to save the secant squared of 3 of x, because we knew further down the line we want to do u-substitution with a tangent, and du would give us secant squared of something if we're taking the derivative of tangent. So we wanted to save a secant squared so that way we could cancel it further down the line. Do your typical substitution, you'll see that the secant squares cancel, and now we're left with a very simple integral in the u world. Use the power rule, get to here, substitute your u in, and get the final answer. So we see a lot of parallels between this problem and the one that we saw with sines and cosines. And in fact, the guidelines are kind of similar. It's just being strategic about what you have to save and what you don't save. So that is the guidelines for that. Let's try a couple of problems on our own. We want to evaluate the following integral, the integral from 0 to pi over 2 of cosine cubed of x over the square root of sine of x dx. I don't really like working with square root symbols, especially when there's a trig function within them, so we can convert that to a power. The square root is equivalent to something to the 1/2 power. Since it's in the denominator, it'll be to the negative 1/2 power. So we can convert this integral into the integral from 0 to pi over 2 of cosine cubed of x times sine of x to the negative 1/2 dx. And sometimes I might write like sine to the negative 1/2 of x, which is not superb notation, but in case I do that, it's just for you to know it's the same thing as sine of x to the negative 1/2 power. So that's what we have to deal with. How are we going to solve this? Let's look at our guidelines. So the guidelines say, if one of the powers is 1, try using u-substitution. Our powers were 3 for cosine and negative 1/2 for sine. So guideline 1 won't work. If the power of sine is odd and positive, it's not, so we can't even look at guideline 2. Guideline 3, if the power of cosine is odd and positive, it is, it's 3. Then we're going to save one cosine and convert the rest to sines. Let's do that. Scroll back down. So this will be equal to the integral from 0 to pi over 2. I want to save one cosine. So let's save one cosine of x. That leaves us with 2 more cosines, a cosine squared of x, times sine of x to the negative 1/2 dx, right? These two terms multiplied together give us this cosine cubed of x term. And we're going to save this pink cosine x. Now we want to convert the rest of the cosines, into sines. In order to do that, we'll leverage the fact that sine squared of x plus cosine squared of x equals 1, so that means cosine squared of x equals 1 minus sine squared of x. So let's do that substitution. This will equal the integral from 0 to pi over 2 of cosine of x, which we'll still save, times, we'll substitute that 1 minus sine squared of x back in, and we still have that sine of x to the negative 1/2 power. And now this might look slightly familiar to the example we saw before, where we have the saved term, we have the substituted term, and we have the leftover term. And what we did was we distributed the leftover term into this substituted term, and then later on we substituted the save term into the conglomeration of everything else. So let's substitute that sine of x to the negative 1/2 inwards, and we'll get the integral from 0 to pi over 2 of cosine of x times, let's see, sine of x to the negative 1/2 power times 1 is still sine of x to the negative 1/2. And then we're subtracting sine of x to the negative 1/2 power times sine of x squared. Same base, the powers will add. So 2 plus negative 1/2 is 3/2. So this will be sine of x to the 3/2 power dx. And now we'll multiply this cosine of x term into both of these and see what we get. 0 pi over 2. We have sine of x to the negative 1/2 times cosine of x minus sine of x to the 3/2 power times cosine of x dx. And we can split this integral into two, so we'll just move the minus, or we'll add in this dx, put a minus sign, and add the integral, and that's equivalent. Now we have these integrals to work with, and this should be a little bit nicer. In fact, if we look back at our guidelines, the first guideline is if one of the powers is 1, try using u-substitution. And indeed, we see in both of these integrals, we have a trig function whose power is 1. And it says u-substitution, so we also have to think about which u do we want. We do not want to set u equal to this cosine of x term, because it's this other funky term that we'll have to cancel with, and the power makes it not great to cancel with. So we're going to set u equal to the base of the funky term. So in this case, we'll let u equal sine of x, and in the second integral, we'll let u equal sine of x. So let's try doing this simultaneous integration. We know we're going to use the same u for both, so let's try doing that. We have u equal to sine of x, which tells us that du is equal to cosine of x dx. So now our integral simplifies to 0 times, actually I'm not even going to write the limits. We'll take care of the limits later because we're switching variables into the u world. If you want, you could change the limits to be in terms of u, so you would plug u in for x here, so the bottom limit would be 0, and then you go up to 1. You know what, let's do it, why not? I'm feeling good. U equals 0 to u equals 1, because sine of 0 equals 0, and sine of pi over 2 equals 1. Let me just move these over so I'll have some room. And then we're going to have sine of x to the negative 1/2 power, but now it's going to be u to the negative 1/2 power times the cosine of x remains, and then dx turns into du over cosine of x. And then we subtract from that the integral from u equals 0 to u equals 1 of u to the 3/2 power times cosine of x times du over cosine of x. There's a lot of colors going on, which makes it super hard to write, but I hope that clears things up, where the green color is what we did with the u-substitution, the blue color is from whatever was from before, and the purple are our limits. That's the color scheme. We see that the cosines of x in the first integral cancel, same with the second integral, and now we're left with some simple integrals in the u world. So this is going to equal the integral from u equals 0 to u equals 1 of u to the negative 1/2 du minus the integral from 0 to 1 of u to the 3/2 du. Got a nice little power rule here. So for the first one, we raise the exponent by 1/2, negative 1/2 plus 1 is 1/2, and we divide by that new exponent. So dividing by 1/2 is the same thing as multiplying by 2. So we get 2u to the 1/2, evaluated from 1 down to 0, minus 3 halves plus 1 is 5 halves. Dividing by 5 halves is the same thing as multiplying by 2/5. So 2/5 u to the 5 halves, evaluated from 1 down to 0. And you can substitute it in, subtract, you'll get 2 minus 2/5, which is equal to 8/5. So this is a really nice problem because we got to see so many new things at once. We tried out simultaneous integration, which is pretty cool, saves a bit of time. But the key thing here is splitting apart that cosine cubed of x into two terms and then substituting in using your trig identities. We have all of the skills to be able to solve these kinds of problems. It's just knowing when and how to use them. And for that, the guidelines come into play. The guidelines are very, very helpful. But you see, you still have to be on top of your stuff. You still need to know u-substitution to be able to solve this. It's not as simple as just, oh, do this one small thing and you're done. No, you still need to know u-substitution and things like that. So things are starting to get more complex, so hopefully you're sticking along. Let's do another problem. The integral of cosine to the fourth of 5 of x dx. So we have a cosine in there, there's no sine. Let's scroll up to our guidelines and see what to do. Note that the power of cosine is 4. So we scroll and we see here, okay, if one of the powers is 1, that's not happening. So we can't do guideline 1. If the power of sine is odd and positive, there are no sines, so its power is like 0, so it's not odd and positive, so we can't do that. If the power of cosine is odd and positive, the power of cosine was 4, which is not odd, so we can't do that. So we look at guideline 4. If the powers of both the sine and cosine are even and non-negative, which they are, use the half-angle identities to convert the integrand to odd powers of the cosine. Goodness me, we have to use half-angle formulas. Let's see. These are our half-angle formulas, these last two right here. So which one do you think we'll use? I think we'll use this second one because it has the cosine term in it, which is what we're dealing with. So I'm going to copy this, and let's jump down here and paste it. So this is what we have to deal with. How are we going to approach this? Well, we can split apart cosine to the fourth into cosine squared times cosine squared. So we can say that this is equal to the integral of cosine squared of 5 of x times cosine squared of 5 of x dx. And now we can use the half-angle formula for both of these. We see a cosine squared, which we can substitute in. A in this case will be 5. So we're going to put this in for both of the terms here. So let's see what happens. Let's just evaluate cosine squared of 5 of x on its own and then do the substitution. So this formula tells us that cosine squared of 5 of x is equal to 1 plus cosine of 2 times 5 times x divided by 2, which is equal to 1 plus cosine of 10x divided by 2. So let's substitute that in for both of these terms here. So we have the integral of 1 plus cosine of 10x divided by 2 times 1 plus cosine of 10x divided by 2 dx. Now what do? Let's try to multiply those two fractions just to be left with one fraction. So this will be equal to the integral of some massive thing. The denominator will be 4. 2 times 2 is 4. The numerator will be 1 plus cosine of 10x times 1 plus cosine of 10x. So you can FOIL that out, or whatever you call it. You should get cosine squared of 10x plus 2 cosine of 10x plus 1. Let's just get rid of the denominator by splitting it amongst the terms. Something like that. So this will be like 1/4 cosine squared of 10x plus 1/2 cosine of 10x plus 1/4 dx. And in fact, we can split that up into multiple integrals. 1/4 cosine squared of 10x dx plus the integral of 1/2 cosine of 10x dx plus the integral of 1/4 dx. And now we have to solve these three integrals. So the last integral, the integral of 1/4, that should be pretty easy to solve. The second integral should also be kind of easy to solve. It's just a cosine term in there. We can use some u-substitution with the 10x, and then we should be in good shape. The first integral, maybe not so easy. It's a cosine squared term. So what does that mean we have to do? Well, if you're saying, look at the guidelines, that would be a good start. Let's scroll back and look at the guidelines. So it's not the first guideline, not the second, not the third, it's the fourth one again, which means we have to use the half angle identity again. So let's do that. Now we have cosine squared of 10x, whereas before we had cosine squared of 5 of x. So I'm going to erase what we did with cosine squared of 5 of x, and now compute cosine squared of 10x. So this will be 1 plus cosine of 20x all over 2. And we can substitute that in. So let's only solve this integral, and then we'll come back to the other two later. So the integral of 1 over 4 cosine squared of 10x dx is equal to, I'll bring out the 1/4, and then we're left with the integral of 1 plus cosine of 20x divided by 2 dx. We can split apart the integral into the integral of 1/2 plus 1/2 cosine of 20x, and then that can be split apart into two integrals as well. Like so. And now we can substitute what we just solved here back into here, and then we're left with a bunch of integrals that are easy to solve. So this will be equal to 1/4 integral of 1/2 dx plus, I'll bring out the 1/2 to make it 1/8 integral of cosine of 20x dx plus the integral, or 1/2 the integral cosine of 10x dx plus the integral of 1/4 dx. So the first and the third integral should be pretty simple to solve. It's just the second and the third one. But they both look pretty similar, where it's cosine of something, and as I alluded to earlier, we should probably use u-substitution. So let's try to do some sort of simultaneous thing, or like we'll try to solve both of them at once. So the first integral will let u1 equal 20 of x, which tells us du1 equals 20 dx. For the second integral, we'll let u2 equal 10x, which tells us du2 equals 10 dx. And now we can solve these integrals. So the integral of 1/2 will be 1/2 x, multiplied with a fourth gives us 1/8 x, plus 1/8 the integral of cosine of u1 times du over 20, and then we add to that 1/2 the integral of cosine of u2 times du2 divided by 10, and then the last integral is just 1/4 x. We can combine the first and the last term into 3/8 x, and then we're adding to that 1/8 times 1 over 20, so we can change that to 1 over 160. The integral of cosine of u1 is simply sine of u1, but we can just substitute whatever we let u1 equal to, which was 20x. We add to that 1 over 20, because this 1/2 and the 1/10 term combine. The integral of cosine of u2 is equal to sine of u2. u2 is equal to 10x. So this entire integral evaluates to 1 over 20 sine of 10x. And then we took care of the last term. This was an indefinite integral, so we need a plus c term. And that is our final answer. What an answer. It's a huge answer. But But look at that, we needed the half angle formula twice. So you can see that these integrals can be tricky because they take a lot of steps. So it's very important to be organized with your work. I'm not very organized, as you can see, but small things like this, where you subscript the u with u1 and u2, if I just let both of these be u, then there's a good chance that when I was solving these integrals, I might substitute the wrong u back into it. With u1 and u2, I can do it more confidently. So these are just like small tips to make sure you're organized well. Some things like this where you have the sum of a bunch of integrals, but you only focus on one and solve that off to the side, that can also be helpful. I don't know, maybe that helps out. But there you go, another problem. And you can see that both of these problems, they're quite long. So if you like integration, you're in for a good time. Let's do another one. Integral of tangent cubed of x over square root of secant of x. This is kind of reminiscent of this first problem that we did here. In terms of structure. So we expect the solving experience to be similar as well. So the first thing we did here was we brought the square root term in as a power term. So let's do an identical thing. So we can say this is the integral of tangent cubed of x times secant of x to the negative 1/2 dx. Now let's look at our guidelines and see what to do. Remember, the guidelines really focus on the power of the term, so let's remember that the power of tangent is 3, the power of secant is negative 1/2. Scroll back up. If the power of secant is even and positive, it's not, it's negative 1/2, so we ignore guideline 1. If the power of tangent is odd and positive, it's 3, so it is. Save a secant tangent and convert the rest to secants. Okay. So, we want to somehow convert our integrand into some form of secant x times tangent of x, the term that we save, times something else. And that product should equal tangent cubed of x times secant x to the negative 1/2. Well, if there's a tangent x being multiplied with something such that we get a tangent cubed of x, we should have a tangent squared x term on the left-hand side. Now we have to take care of the secants. When we multiply secants, the powers will add. So the power of this here is 1. We have to multiply it with a term such that when you add its powers, 1 plus that power should equal negative 1/2. So 1 plus negative 3/2 equals negative 1/2. So we'll multiply this with secant of x to the negative 3/2 power. So what we just did is we took our integrand and we decomposed it in such a way that we have a secant tangent term available and it's being multiplied with something left over. So that, in fact, is going to be our new integrand to work with. So we're finding the integral of this. So that's what it means by save a secant tangent term. Just as before, where we saved a, up here we saved a cosine term, here we're saving a secant tangent term. It might require a little bit more computation, but it all works out in the long run. Let's go back to the guidelines and see what it said. It said, save a secant tangent and convert the rest of the tangents to secants. So we had a tangent squared term. We know tangent squared equals secant squared minus 1. So let's do that substitution. We're left with the integral of secant x times tangent of x times, we'll replace tangent squared of x with secant squared of x minus 1. And then we'll multiply that with the leftover term. And again, you see that pattern where you have the saved term, the substituted term, and the leftover term. So we're gaining these patterns, which is a really good sign. And then, as we did in the previous problems, we'll first multiply the leftover term inwards, and then we'll multiply the saved term inwards, break up the integrals, and solve. So let's first do the distribution. we'll keep the secant tangent term, and we're multiplying that secant x to the negative 3 halves, so we get secant of x to the 1/2 power, because 2 plus minus 3 halves is 1/2, and then we subtract secant of x to the negative 3 halves power. Good. Now we could distribute that secant tangent term in, or no, let's do that. Let's do that. It'll make it a little bit more understandable. So we have to distribute the secant x tangent x term in. So we multiply that by secant x to the 1/2, and then we subtract secant x tangent x times secant x to the negative 3 halves dx. And we can split this apart into two integrals, so I'm just going to try to do that to the best of my abilities. Okay, that works. And now we have these integrals to solve. We can do simultaneous integration here, and the way we can do it is with u-substitution. Remember what I said before, we want to choose a u that, has the funky power with it. So in this case, the funky powers are the 1/2 negative 3 halves. So we'll choose u as secant of x for both of them. And that's a good choice of u, because when we compute du, the derivative of secant of x is secant x tangent of x. So we would be in good shape in that case. So let's do that. In this case, we don't have to be clean with setting u1 equal to something and u2 equal to something, because for both integrals it's the same u. So we'll let u equal secant of x, which tells us that du equals secant of x times tangent of x dx. And now we're going to substitute in our integrals. So we get, I'm going to try to be good with the colors here. Integral secant x times tangent of x, our saved term, multiplied with u to the 1/2, and now dx becomes du over secant x tangent x for the first integral. For the second integral, similar thing. Secant x tangent x stays from before. The secant of x becomes u. We're setting that to the negative 3 halves power, and dx becomes du over secant x times tangent x. And you can see now why we saved that red secant x tangent x term in the very beginning. All of that just to be able to cancel with this in the denominator. So this cancels with this cancels with this. We're left with two beautiful integrals in the u world. Du minus integral of u to the negative 3 halves du. We've made it this far, just don't mess up your power rule. Add 1 to 1/2 to get 3 halves, divide by that new power to get 2/3 u to the 3 halves, minus negative 3 halves plus 1 is negative 1/2. Dividing by negative 1/2 is the same thing as multiplying by negative 2, so we can make the negative a plus sign, 2u to the negative 1/2. And now we just have to put our u back in. We set u equal to secant of x, so this will be 2/3 secant of x to the 3 halves plus 2 secant of x to the negative 1/2. It was an indefinite integral. Don't forget your plus c. That is our answer. So I was right. It was reminiscent of that first problem we did. Similar pattern of that saved term, substituted term, leftover term, and doing this simultaneous integration with the u-substitution. If you're not feeling good with this simultaneous u-substitution, that's fine. Just solve these integrals one at a time. You know how to do that. I'm just doing that to speed things up just a tiny bit. But there you go, an example with tangents and secants. And now we'll move on to, I believe it's the last question. Yes, it is. A seemingly simple integrand, you would think. We'll see if that's the case. The integral of secant cubed of pi of x dx. Let's scroll back to our guidelines, see what we have to work with. Remember the powers. The power of secant is 3, and the power of tangent is 0. We know secant and tangent go hand in hand, so we'll just say tangent is 0. Scrolling back up, if the power of secant is even and positive, it's not. Let's go to the next guideline. If the power of tangent is odd and positive, it's not. Third guideline. If there are no secants, there are secants. Not that. Fourth guideline. If the integral is only secant with an odd positive power, use integration by parts. You thought we were done with integration by parts. No, we're not. We are going to do some integration by parts for this problem here. So we need to choose a u and a dv. Let me just write down integration by parts again. U times dv is equal to uv minus the integral of v times du. And if you haven't watched my video on integration by parts, go watch that. You have to know integration by parts, and then come back to this. So we have to choose our u and dv. And we need to choose it in such a way such that their product is secant cubed of pi of x. And we need to choose it also knowing that we have to take the derivative of u and take the integral of dv. How do we do this? There's only so many ways to allocate the secant cubed into u and dv. Well, taking the derivative of like secant to some power is not super fun. It'll be like power chain rule type thing. So maybe I would want to give u just like secant of pi of x. So let's just think about that. Secant of pi of x. And then dv would equal secant squared of pi of x. And I'm like, okay, maybe that integral would not be fun to solve for v. Until you realize that the integral of secant squared of x is tangent of x. So we're actually really close there. We just might have to do some u-substitution. In fact, let's just try to solve that integral. If we were to solve this integral, let u equal pi of x, then du equals pi dx. So that means v equals the integral of secant squared of u times du over pi, which is equal to 1 over pi integral of secant squared of u. The integral of secant squared of u is tangent of u, so this is 1 over pi tangent of u, which is equal to 1 over pi tangent of pi x. So that wasn't that bad, to be perfectly honest. Now we can solve for du as well. Du, the derivative of secant is secant tangent, but we have to do the chain rule here. So we'll do pi, so we'll take the, actually no, let's do it the other way. So the derivative of secant x is secant tangent, so we'll do secant pi of x times tangent of pi of x, but then we have to multiply it by the derivative of pi of x, which is pi. So we have our u, we have our du, we have our dv, and we have our v here. Now we can do integration by parts. So this will equal the integral, it'll equal uv, so this would be secant of pi of x, that's u, times v, which is 1 over pi tangent of pi of x, minus the integral of v, which is 1 over pi times tangent of pi of x, du, which is secant of pi of x, tangent of pi of x, times pi dx. I forgot to put in the dx here, and I forgot to put the dx here. Too bad. Okay, let's try to clean this up just a tiny bit and then work from there. So on the outside we have 1 over pi secant pi of x tangent pi of x, and then on the inside, then we have the integral. This 1 over pi cancels with this pi, and these two tangent terms are alike, so this becomes the integral of secant pi of x times tangent squared of pi of x dx. Okay, so how are we going to solve this integral? We see a secant and a tangent squared term. Well, we can use the trig identities to handle that tangent squared term to convert it into secants, and we'll just be left with an integral in the secant world. So why don't we try that, where tangent squared equals secant squared minus 1. So this entire quantity will be 1 over pi secant pi of x times tangent pi of x minus the integral of secant pi of x times secant, I don't want to use that color, I'm going to use pink instead, times secant squared of pi of x minus 1 dx. Now let's just distribute and work from there and see what we get. This is 1 over pi secant of pi of x times tangent of pi of x minus the integral of secant cubed of pi of x minus secant pi of x dx. Okay? You know that when I see these integrands with that minus sign or plus sign in the middle, I like to split it apart into two, so why don't we do that? 1 over pi secant of pi of x tangent of pi of x minus the integral of secant cubed of pi of x dx minus the integral of secant of x dx. And now we have these integrals to solve. We can probably handle secant of x because we learned that a little bit back. What about secant cubed of pi of x? Well, let's take a look at our guidelines. So we can check through them. It's not the first one, it's not the second one, it's not the third one, it's the fourth one. Use integration by parts. Wait a second. Didn't we already do integration by parts? We did. The first thing we did was we solved for the integral of secant cubed of pi of x. And now we're trying to solve for it again. What does that mean? Well, this might be familiar from a previous video, but why don't we just write out what we've solved for thus far? We were trying to evaluate the integral of secant cubed of pi of x dx, and we said, hey, that we know is equal to 1 over pi secant of pi of x tangent of pi of x minus the integral of secant of cubed pi x dx minus the integral of secant of pi of x dx. This should be a pi over here. Oh well. These two integrals are like terms, which means we can treat them as massive variables and bring them to the same side. So this implies that 2 integral of secant cubed of pi of x dx equals 1 over pi secant pi of x tangent pi of x minus the integral of secant pi of x dx. Now all we have to do is solve for the integral of secant of pi of x and divide everything by 2, and we've solved the problem. So even before I finish the problem, the key takeaway is don't forget what you're trying to solve for. If you got to here, and then you start doing integration by parts again to solve this, you're just going to keep on getting stuck. You have to remember that this is what we were trying to solve for. I know, like, it's so easy to forget. We've spent like 7 minutes getting up to this point here that, like, when you spend that much time, you already forget what you're trying to solve for. You need to be cognizant of that fact because that can save you so much time. Let's finish up this problem and finish up this video. We can solve this integral using some u-substitution. We'll let u equal pi x. We'll let du equal pi dx. So let's just solve that integral off to the side in this box here. The integral of secant of pi of x dx is equal to the integral of secant of u times du over pi. So that's equal to 1 over pi, the integral of secant of u du. And if we remember the integral of secant of x, it's ln of the absolute value of secant of x plus tangent of x. So this will be 1 over pi times ln absolute value secant u plus tangent u. Substitute the u back in. Ln of secant of pi x plus tangent of pi x. And now we can substitute that back in. We get 2 integral secant cubed of pi x dx equals 1 over pi secant of pi x tangent of pi x minus 1 over pi ln absolute value secant pi x plus tangent pi x. And now finally we can solve for the integral of secant cubed of pi of x dx by dividing both sides by 2, 1 over 2 pi secant of pi x tangent of pi x minus 1 over 2 pi ln absolute value secant pi x plus tangent pi x. Don't forget your plus c, as this is an indefinite integral. Box your answer, throw down your pen, and go take a nap, because this problem was a behemoth of a problem. That's why integrals can be so fun. A seemingly simple integrand leads to absolute chaos. But as you can see, things are starting to build on top of each other. To solve these problems, you need to know u-substitution, you need to know integration by parts. Take your time to learn these integration techniques and become masters of them. Because if you just seem to kind of understand the topic, further down the road, it's not going to be great, because we keep on borrowing these techniques from the past. They're all going to build together. Those are all of the examples I had for you today, but I think they covered a lot of things. Look over the guidelines. If it helps to memorize the guidelines, do that. Or if you just want to have them as a reference, go for it. They're going to help you out a lot. We use them a lot. I'll just scroll back to them. These are your guidelines for sines and cosines. These are your guidelines for secants and tangents. They're going to be immensely helpful for you. And yes, I hope you learned a lot in this video. I hope you followed along through these examples. In the next video, we're going to continue with these advanced integration techniques. So lots of fun to be had. But until then, I hope you enjoy the rest of your day or night. And as always, take care.